All right. Thank you everyone for tuning in this morning. My name is Carey King. I'm a research scientist and the assistant director here at the Energy Institute at the University of Texas at Austin. My academic background is mechanical engineering, and over the last several years, or almost a decade now, I've been investigating and researching issues related to understanding concepts like net energy analysis and the sort of the flow of energy in the economy at the broad scale, and relating this to other economic trends. And the presentation today is my current culmination of this work in a macroeconomic model that links these ideas together, and is now available in a journal article on Ecological Economics. And at the end, I'll have the link and the title of the paper at the end. So shall I begin the presentation?
Yes.
Okay. So this presentation is essentially summarizing this model I've made, which I called the HARMONEY Model for Human and Resources with Money Model. And this builds off a couple of other concepts and combines them together. So for this system dynamics group and economics chapter, and then the WPI System Dynamics Club, then this is perhaps up your alley of combining several ideas into a unified framework without a tremendous amount of depth into any one of them, but combining them in ways that make sense and produce interesting results and dynamics. So the goals for my sort of pursuit here, research pursuit in macroeconomic modeling, are to understand things like if the finite Earth is affecting trends we see in the world, can be physical flows like energy flows, but also economic trends, things like wages and investment and debt. Can we understand if something about the physical environment or the physical world is affecting these trends? Also, it would be good to understand very broad historical trends, such as data that represent the agrarian to fossil or industrial economy, so the transition to an industrialized economy. Because if we can more effectively do that, then we should have a more effective basis to think about transitioning to a renewable or a low carbon economy. So today's presentation is really the step on the first one, is to have a model that has basic ideas embedded in it that can understand the finite Earth and understand this in a macroeconomic context of other variables. And so that's what I will present today. And to give you a hint of why this turned out to be perhaps more interesting than I anticipated when I was working on the model, is that the model mimics this this is one important trend of, say, the United States economy over the last almost century now. And what this is showing are two things. The black line and the left axis are what's called the wage share, the wages and salaries divided by GDP of the US economy. And it's roughly been flat, let's just say roughly almost 50% from the 1920s until 1970s, and then it's declined somewhat steadily since that time. And this is the basis for people thinking about wage inequality or income inequality, and why this has become such a hot topic over the last 10 or 20 years, is that this trend has been going on for now 50 years. And that coincident with this beginning of a decline in wage share, there was a cessation of the increase in energy consumption per person in the United States. So the red dashed line is just total primary energy divided by population of the United States, and it was increasing until this time in the early 1970s, and then went roughly flat, maybe slightly declining now. And so these trends are coincident, and it turns out my model has something to say about explaining these trends, or at least providing a physical mechanism for why this might occur, and combined with other economic rationales. And I'll also show something about private debt, or at least the debt ratio at the end. So that's kind of where this is all going to go at the end, is to a model that can have something to say about that from a resource perspective. The idea I had was essentially, how do I combine the quote unquote simplest biophysical model, or model of a physical system, with the simplest model of an economy at the macro scale, and link these two together. So some of these ideas often overlap between these models and some do not. Population usually overlaps. Biophysical models look at natural resources, describing natural resources explicitly, maybe have an idea of capital like machines. Economic models usually have often population, capital may be represented as money, may be represented as physical items, but then which is normally different is thinking about economic flows such as wages and how many people are employed, and sometimes debt, depending on the economic framework you use. So these are all important pieces that I wanted to link together. So this slide will now show essentially a structure of the model, at least give you an insight into what's kind of going on behind the scenes without just showing the pure mathematics. So in the model, there is some nature or resources out there. I show a tree here because the model from which I took this is essentially modeling resources as something akin to a forest. So it has a regeneration rate. It can come back, you can extract it, and it regenerates itself. So there's some resource out there. The resource is used to do four things, or three types of things, but really four things in the economy. So there's four separate flows. The first flow here at the top is the nature or resources that are required to operate capital, whose job it is to extract. So K for capital, this type of capital is extraction capital. So this is the capital whose job it is to take things from the environment. So this is like an oil drilling rig or a photovoltaic panel. It's extracting resources from the environment. And an important feedback will be that from a net energy perspective or a biophysical modeling perspective is to understand this feedback to the extraction of nature itself. Essentially, how much energy does it take to extract energy, and how does this feedback relate to the economy? So that'll be discussed later as well. So that's one type of capital. There's only two types of capital in this model, which is to say there's two types of machines, if you will, or two categories of machines that do two different functions. The second type of capital is just what I'm calling goods capital here, and the job of goods capital is to essentially make more machines or make stuff. So in this model, the economy is quite simple. There are only two sectors. There's this extraction sector and there's this goods sector. And both of them need essentially fuel to operate machines. So that's what the nature is. This is just saying that if you do not have energy input into machines, they can't operate. So that's what those two flows are. The bottom flow here is nature for human consumption, so that there are people in the model and they have birth and death rates, and the death rate is a function of how much they consume from nature, essentially abstractly as if they are consuming food, and if they don't have enough food per person, then the death rates might go up. So this has units of physical nature consumption, gets converted into a price, and so it turns into a monetary unit here of consumption of nature, which an economist in a normal macroeconomic model might have household consumption as a monetary flow. The fourth of these nature flows is the nature that's embodied in capital. So as to say, if I'm going to make a machine, or if I'm going to make a new unit of capital, it has to be made of resources that I extracted from the environment. And so though when I make a new piece of capital, then in economic modeling, then that's investment. So I convert that, have a conversion factor from the nature embodied in capital converted to the price to get to a monetary value of investment. Investments there are two types of investments, or two quantities of investment, because there are two types of capital. So there's an investment value for each type of capital. So again, this decision is made in monetary units based upon profits, and this then gets converted through solving for the price of goods, or the price of capital, that is the investment, and gets translated into a new quantity of capital. One final flow that's here is the consumption of goods, or household consumption of goods. So there are some goods produced, some of these end up as investment, and then there are some goods produced that are left over, and these are assumed consumed by households. So essentially there's 3 units in the model. The left side is green, is units of flowing resources. The middle is units of goods. So these are flows of goods, and then the right side is flows of money. And so these are all getting tracked simultaneously within the model. So this is a stopping point if anybody has any questions about the basic kind of structure behind the modeling concept, which is to track these things simultaneously.
Yeah, I'm trying to. So you've got you've a certain amount of nature consumed to produce goods, a certain amount of nature produced for doing the extraction process to produce goods, or to get the resource, right? So that's a resource conversion. Then capital, though, is capital directly from nature, or is it related to the goods or the extraction capital?
Right. Right. Capital in this case is the output of the goods sector. So the goods capital makes itself. The goods capital makes more goods capital, I guess.
Okay. Yeah. It's just the way you're at. It's just I'm trying to your little diagram here.
Right. Yeah, I could have put, I guess capital comes out of the goods capital sector instead of goods, but yeah. So it's generic in that sense. The goods sector is essentially, the sector that does everything else in the economy, and there may be many ways we could conceive of that. But it makes new capital, and then if it operates more than, if it produces more goods than are required to fulfill the new capital investment, then whatever's left over is consumed by households. So in the model, some equations later, you'll see that essentially household consumption, I assume, is just a residual or leftover from whatever is needed for investment. So the economy is producing so much nature resource extraction, it's producing so many new machines, and then whatever's left over goes to households.
And just to clarify, Dr. King, is the unit of energy here, is that K? Because you've got dollars of goods, you've got K of good. Where is energy, or will you get to that in a bit, where the energy is being tracked here?
A bit, I guess here I'm using it as nature, so it's kind of generic. So you can think a forest is maybe a good analogy. So I can burn the wood and it's like fuel and energy, or I can use it to construct something like a house. So the model here is so generic that resources in the environment are representing essentially anything we might use environmental resources for, which include energy and structural materials, I guess.
So would it be fair to say that the green flows are the use of energy, and then the other ones are sort of how that energy gets used and creates or gets transferred into material things?
Yes, for the most part, yeah. So
Okay.
the green are essentially, the 4 flows of green are me saying that it gets allocated amongst these 4 flows, and these are the only 4 flows that energy gets allocated.
Great, I'm tracking.
Yeah.
Thank you.
Yep.
The flow from extraction capital to the environment, this flow there, is it for the regeneration for the nature, or it's more like depletion from, let's say, pollution or climate change, or both?
I have no concept in here related to pollution or climate change. So this is what I have here, and what this model is purely a discussion of the physical requirements to operate the economy. And one of these physical requirements is that capital requires energy as an input to do something.
Okay.
So that's, yeah. So those are all added things that could be added. Things like pollution or climate change could be added, but they're not here.
Okay.
Yeah. Okay, good question. So anything else? Go ahead. All right. So I'll just summarize a little bit what's behind the ideas behind the biophysical modeling and the economic modeling in terms of the mathematics. So some of you may have seen this paper, is a 2014 paper called the HANDY model for human and nature dynamics model. It essentially has 4 equations. There's 2 types of, it's modeling an agrarian society, if you will, something like this. And it's got 2 equations. There's a population of workers. There's a population of elites, which are essentially defined as people that don't work and that consume more than workers, or consume at a higher rate than workers. There is nature. Nature, again, is like a forest, so this is where I take that from. It the rate of change of nature is its regeneration minus how fast you extract it. And then they have a term called wealth, or an equation called wealth, which is essentially nature you've extracted, but you haven't consumed all of it yet. So the accumulation of wealth is how much did you extract minus how much are you consuming, and so you can accumulate this wealth. So this is this is essentially in my model an inventory of nature that you've extracted. You can think of it as a pile of wood on the ground that you haven't done anything with yet. So in my model, I simplify. I get rid of the elites to just
You go back to
simple
the
model. Oh, right. So this is, go ahead.
Versus consumption. So, I mean, the extraction process itself is lossy, right? So, do you have a concept of that? Meaning that, you know,
A concept of like something like energy efficiency losses or something, or?
I mean, any kind of you don't have perfect conversion processes, right? The extraction itself, I guess it doesn't really matter. It's just embodied. You have extraction versus
right. I'll show. The answer is yes, but maybe not exactly in the way you're thinking, or maybe not even exactly in the way I'd like it to be represented. But there is an idea of how much nature does it take to operate a unit of capital, and inherent in setting that number, there is an unspecified, I guess, if you will, conversion loss in some sense. So it's not an efficiency where we might think about a pure conversion in that sense, but it's a conversion of basically how much fuel does it take to operate a power plant, you could say, without specifying the conversion loss.
Okay, right.
So that's in here, but not shown yet. I'll point out that factor later. Okay, so this is just generically in words what is going on. In equations, what is going on. So I get rid of the elites just to simplify the model, which means I get rid of the consumption of elites at the bottom right in the wealth model. And so I'm describing the handy model here and I modify it, but this gives you a feel for what's going on. So in the handy model, there's this parameter lambda. Again, the resource, the natural resource, is like a forest. So this lambda represents the maximum size of the resource. So this would be the maximum number of trees that are possible. Maybe inherently something like a extent of the limit of land or the size of land. So this is the parameter which says this is how big the world is in some sense. So there's basically this specifying that. There is a regeneration rate, this gamma, so how fast does it grow back? If you set it to 0, then you have a fossil resource, effectively. It can't grow back. There is this extraction rate. So this is the equation from the handy model. And so it has a parameter delta, which is a parameter you can play with, sort of like a technological parameter or something to play with sensitivities in the model. There's the X, which is the number of commoners, so the number of people, and then Y, which is the amount of nature. So essentially saying you need people to extract nature because this is like an agrarian society, and maybe they're effective at it for a high lambda or high delta rather, or they're maybe not so effective. And what this does is essentially get you a feedback that makes it such that as you extract a resource and deplete it more fully, you can't extract anything else. So if Y goes to 0, or if nature goes to 0, then extraction must also go to 0. So in some sense, this is maybe the simplest way to represent that feedback. I make this a function of capital instead of people, but I also have people that have to work to operate the capital later to try to relate it to a little bit more of a modern economic context. And another important part that I mimic from this model is the death rates, or alpha is the death rate, which is in their model is a function of wealth. So how much wealth is there, which is per person dictates the death rates. I make mine a function of nature consumption per person. So the death rate is basically the same idea that they use, but instead it's a flow rate of nature per person, or household consumption of nature per person, that dictates the death rates. And to be simple, the birth rates are constant. So that's a little bit of the background of the math. Now, if this is essentially a predator-prey model, if you will, or Locke de Volterra model of humans as the predator and nature as the prey. If you have this extraction parameter delta, if it's not too large, you can end up with this type of situation just from their paper, where you end up in some steady state. Nature is getting extracted at its regeneration rate. The number of people, commoners on this chart, goes up to some amount and remains steady, and the quantity of wealth goes up to some amount and also remains steady. So this is just a kind of standard result you can get from this type of model. If you increase the extraction parameter or make it larger, which means you're extracting nature at a higher rate per person, then you can extract the nature so fast that you extract it before it's able to regenerate itself, and you essentially collapse the society. So essentially, I was looking for the simplest biophysical model I could find that had the ability to essentially collapse the economy from a lack of resources, and this is essentially it as far as I was concerned. So this had the basic pieces I needed, and I wanted to add the economic context to it. So what are the major pieces of the economic model, or at least we may call it an economic growth model? There are, as mentioned in the diagram, there's two types of capital K. So the rate of change of capital, this is kind of relatively standard stuff here, is investment minus the depreciation of the capital. So this describes the increase of the capital stock. And it's in physical units, so like physical units of goods are capital. So that's why investment here would be in units of money, I, divided by the price of goods. That's kind of the price of capital, so that gives us units of capital in physical units. There is the concept of debt. So debt is, this is essentially like private debt, like commercial banks lending money to businesses to invest, and they might, businesses invest more than their profits, and I'll show this in a second, then they would take out a loan to do that. So that's what is represented here by this debt. So it's essentially investment minus the depreciation, or oops, net investment, which is the inside the parentheses, minus the net profit of the company. So if you invest more than your profit, then you would take out a loan for that purpose. So I track that for each sector separately. And the physical output of each sector. So again, one sector is extracting resources, so its physical output is the flow rate of resources. The other sector is producing more machines or goods, and so its output is the amount of goods. They both have this framework, Leontief sense. So it's capital times the capacity utilization, which is the CU. How often is the capital operating, and that adjusts in the model to make sure that the resource flows are balanced in a sort of conservation of flow sense. There's some productivity parameter or capital output ratio for each sector, and this one varies for the extraction sector for the net energy reasons, which I'll get into. And so that's either limited by capital or it's limited by labor. And then for labor, I just assume labor is multiplied times some labor productivity, which for the purposes of this model so far does not change. So there's no exogenous assumption of increase in labor productivity. So how is investment defined, or the behavior of investment of the two sectors? I take this kind of framework from Steve Keen, and some other people have used this as well, and sort of this post-Keynesian economics literature. Essentially, investment in my model is some multiplication parameters, these kappas, times depreciation and profit and net profit. So you're either investing, these are parameters I play with, which I'll describe the implications of whether you invest at a high rate or a slow rate, and that's essentially dictated by whether these kappas are relatively large or relatively small. But essentially, we're talking about investing as a function of profits. And so here is an example of data from the United States about investment relative to profits. And it's the same data on both sides of the slide here, but presented in different ways. On the right side is investment divided by profits over time. So you just see the time series for the United States. And I'll just click the button here. So you can see if it's a 1, this means that the economy overall investments are equal to profits. But you can see that traditionally we invest significantly more than profits. say 50% up until the 1970s. Then it rose and fell there over the course of the last 4 decades. The only time it's been less than 1 has been in World War II. So you can see the slide on the left, or the picture on the left. The y-axis is investment divided by GDP. So investment as a fraction of GDP, and then the x-axis is profits as a fraction of GDP. And so if you're in the shaded yellow area, you're investing more than your profits, and you're making net profits for the economy overall. So the Great Depression is the only time in which profits were, at least in these data, less than 0 or negative, and World War II was the only time when investment was actually less than profits. So I use this as a basis to think about the kappas, or the amount of investment relative to profits, when I run the model. So there's wages in the model, and wages a cost to operate the sectors. Here, wages, this is kind of a quasi-Phillips curve idea, if you're familiar with that, but essentially wages are a function of employment. So it's an exponential function that I use, so that's just graphically mimicked here on the right. So, the idea is that the more people are employed, the more ability they might have to bargain for wages or switch jobs and get a higher wage. So as the employment fraction goes up, the rate of change of wages for this function would be positive, multiplied times the current wage, and increase the wage. If there's not a lot of people employed, then they might be able to not ask for higher wages, and so their wage might go down. So this is embedded in there, but it's constrained by the resource flows and the structure of the model. So even though in the end I'll have a high employment fraction, wages do not necessarily go up in a real wage sense. Are there any questions on any of those parts? Okay, so here, this is, I'm going to use this not to go over it in detail, but to summarize the sort of net energy feedback of the economy. So this is kind of a standard, input-output table representation of flows in the economy, where the columns represent inputs or purchases by each sector, and the rows represent outputs or monetary sales of each sector.
Is it like a stock flow consistent, this table here, or it's a bit different?
I do use sort of the stock and flow consistent modeling or accounting, yes. So that's not represented in this slide, but yes.
Okay.
So this is all, I guess, a different way to, well, it's a different way to show the data. But so yeah, there's two goods. As the goods sector and the extraction sector. The upper left gray 2x2 matrix is the sort of input-output matrix, or the intermediate exchanges within the economy. And so I'll focus on this one. So this the extraction input required to operate the extraction sector. How much, essentially, this AEE term represents the resources required to operate capital, again, whose job is to extract resources, divided by the total resource extraction. So we can think about this as total energy consumption of the resource sector divided by the total energy extracted in the whole economy, or total energy consumed in the whole economy. So in the mathematics, this is represented in this way, and this was to the question earlier. So the numerator is a parameter eta, which is not really an efficiency. I use eta, but it is the amount of resources required to operate the capital at full capacity utilization. So multiply that times how much capital there is times how much capital is being used, and then that says this is how much resources is required to operate it. Inherently assumed in there, but not explicitly specified, is efficiency conversion factor or something like this. So that's the numerator. The denominator is the expression somewhat modeled on the handy model for the rate of resource extraction, which is delta, some parameter to play with potentially, y, the quantity of resources, and then again times the capital and how much the capital is being used. So the capital and capacity utilization sort of cancel out, and you end up with the middle expression, which tells you, because this parameter has the same units, resources divided by resources, it is limited by 1. The smallest, or the maximum number that this can be is 1, which would mean you're consuming all of the resources that you are extracting in order to just to operate the extraction capital only. So this means that no other capital is getting operated, and there's nothing left over for household consumption. We'll see this later. So you can understand these parameters to essentially specify why you cannot extract all of nature. So for example, if nature Y went to 0 in this expression, then you would have an infinite number of resources required to operate extraction capital. And of course, it's not possible. So, so this limits what the minimum nature extraction can be. You can't extract all of nature because of this assumption here. You will economically, or you will physically not be able to extract the last bit. Okay, so that's what I just said here. So this AEE is the key to understand this net energy concept, or how much energy it takes to run the energy sector, and why you can't actually extract all of nature, and the economy could collapse because of this concept. All right, so prices, I'm not showing the details here, but prices for each sector, so prices for goods, which are capital, and prices for nature are assumed as just a markup on the costs. And for the results I'll show you today, I'm just assuming a constant markup. The paper also has a variable markup, which has the more moderating feedback, but it turns out the constant markup assumption is the one that presents interesting results to compare to trends in the United States. So there's a series of costs, wages, interest payments. So here's a little bit of breakdown what the cost factors are. So the cost per unit, again, per nature and per good for each sector are listed at the bottom. And the pieces are, this is kind of a full cost accounting approach, I guess. Depreciation, some depreciation factor delta, try not to get confused with the previous delta that affects extraction. They're two separate numbers. Times the price of goods, times the quantity of goods. So there's a quantity of depreciation. There's interest payments on debt. So if companies, these sectors are taking out loans to invest, then there's some interest rate. It's just a constant in my model that is part of their cost of doing business. There are labor costs, so wages, W times the labor, how many people are employed. And then there are the intermediate purchases of goods and nature. So there are intermediate costs for each sector as well. So these are the full suite of costs to operate the model, and the prices are just say 7% higher on top of these costs. But I solve for these prices simultaneously in the model. So are there any questions there before we get into the results?
We good?
Okay, so all right, so I'll show the results, and recall that this model is not calibrated to anything. So I'll compare in the end to U.S. trends, but it's not calibrated to the U.S. numbers. It's not calibrated to anywhere. It's sort of at this, just abstract model construct level right now.
But
so
from there, for your model, so you said it's not calibrated, but how do you choose your parameters for the model?
It's a good question. I mostly have parameters following the handy model, and then I have a lot of new pieces to the puzzle. So I chose them to be representative of at least some things realistic. Say for the wage function, I have to pick some amount of some level at which the wages would increase relative to employment or not. So it's 65% participation rate in the economy is that number. There was not a systematic approach. The model is, the settings of the parameters matter in the sense that they can't just be anything, but because they have to match in the initial conditions. But right. There wasn't a systematic goal in mind to set them, but in the end I set them as needed to make the model work, I guess, is the short answer. But yep. That's So as good as I can say at this point. So yeah.
Thank you.
So here's the sort of causal effects, if you will, assumed in the model. So the driving factor is the assumption or behavior assumption about investment. So sectors invest in new capital based upon their profits and setting a parameter related to that. Then I calculate how much labor and employment, how much labor is needed. Then you know what the employment is. Then you know how to update wages. Then you look and see, okay, which one is the limiting factor? Is capital limiting the output, or is labor limiting the output? So you'll see the effects in the results, that there's a maximum number I put on what percentage of the population can be employed. So we'll just say 80% is the maximum amount of the population that can be employed, because there's children and elderly people, even though I'm not explicitly modeling demographics in any way. So in that sense, it's arbitrary, but you know it has to be between 0 and 100%. So looking through that, then you know you can calculate the gross output of each sector, and therefore the net output of each sector, which is just total output minus the intermediate demands of each sector. And then in the end, you end up with saying, okay, here's how much is left over in household consumption. So this is an assumption in the model. So household consumption, big C, is essentially net output Y minus I, investment, and a change in value of inventories. So that's getting, this consumption equation is getting, of course, calculated in monetary units and also converted via prices to physical units as well. All right, so here's the results. Again, a constant markup assumption for prices. So there are two trends I'm going to show you in most of these charts. It actually has three trends. The dotted line is, well, I'll just go through them here. So the investment level is relative to profits and depreciation. So again, investment is defined by a parameter multiplying times depreciation plus some parameter multiplying times profits. And so a low, when I say a low level investment, that just means those parameters are relatively low, and a high level means they're a little bit higher. And you end up with a threshold of different results. So the solid line in all these charts will be the high investment case. The dashed line is this low investment case. And the dotted line, which I won't harp on too much, or I won't discuss explicitly, is a fossil resource assumption case, where I assume the regeneration rate of the nature is 0, and so it's treated like a fossil resource. The main takeaway on that is that essentially throughout the results, if you were just to look at the results and not know anything about the model, then you could not effectively tell the difference between if you had a renewable resource and you just were not investing enough, or if you had a fossil resource. You essentially can't tell the difference. They have the same qualitative response. Okay, so the takeaway from the renewable low case, or not investing enough, is that if you don't invest rapidly enough, alternatively, if the price markup is too low, you get the same result for a low price markup, the system will collapse, or essentially you end up with this rapidly collapsing situation. But if you do invest high enough, then you end up in I put it in quotes here, stable. It's not essentially stable in the full steady state, stable sense of all states. But you end up in this more stable situation if you do invest fast enough, or you do have a high enough markup.
So,
and we'll go over this throughout the rest of the results. But go ahead. Question.
Just a quick question. So the investments, you have an inflection point there. It's pretty rapid. Is that the only? I don't know if you've tried other combinations of investment timing. Is that investment done as a discrete input or to the model, or
the investment? Yeah, the investment rule never changes in the model. I guess you could say there's they're going to assume to invest a certain fraction of their profits, and this doesn't change.
That's an interesting dynamic path.
Right. Yeah, and I'll go through more details of it here. This is just looking at the resource the natural resources here. This particular chart is how much nature is in the environment still, is what this chart is. I didn't say that.
Yeah,
so in the quasi-stable.
That's into a stability point. It's just interesting.
Right. I'll go into why this is, and this has to do with whether you hit maximum employment or not, or the rate. It has to do with relating to the rate of population growth. So I'll go into that. So this here's a way to try to understand the difference between these 2 points, and there'll be several slides going into it. This is participation rate, so the fraction of people that are working in the model. And if you have a relatively low investment rate, so let's just say investment is covering depreciation and is 1.3 times the net profit, then that's this result here with this sort of rapid collapse. It never reaches 80% participation rate. If you have a high investment relative to profit, say 1.5 times the net profit, then you essentially do reach the maximum participation rate, and you end up with this labor constraining situation in terms of producing output. And then with low investment, you never end up in a labor constraining situation. You have you're always constrained by the quantity of capital that you have, and so you keep trying to invest in capital. So the next slides will explain this in more detail, but this is an important point to look at. So how do we think about that? So here at the top of the slide is my short version for how to think about this. If you have low investment, then essentially the model, you accumulate more people. They're a stock, and capital is a stock. You accumulate more people but less capital. If you have a high investment, you accumulate fewer people and more capital. And this, in some sense, makes sense. The faster you invest, the more capital, by definition, you're accumulating. So in the low investment case, the dashed line on the right, this is the population. You end up with a higher peak population. And then in the high investment case, which is the solid line. And in the right or the left side chart is the total amount of capital. So both types of capital added together. You end up with the solid line. In the high investment case, you have more capital at any given time as you're investing than the low investment case. So that part's intuitive, but the less obvious part is that it has a relation to population that affects the dynamics in this way. So here's the low investment case, which I'm going to just kind of highlight here. Here's the price of resources, or the real price of resources in the model. So again, the dashed line is the low investment case, and the price of resources just sort of exponentially or start increasing. And so if this price of nature is rising rapidly, and then the system collapses, the way to understand this is from the net energy context, or at least one way to do it. So I have this NEPR, or net external power ratio. Some people use this, refer to this term as energy return on investment, but it's essentially, as specified on the left in simplistic form, net nature extraction, how much nature is getting extracted minus what the nature extraction sector requires itself, divided by the total extraction of the nature extraction sector. So just pay attention to the black lines here on the right side. So this is a ratio of essentially energy output from the net energy output of the sector divided by what it needs to operate itself. If this goes to zero, then it's consuming all of its output essentially just to keep itself operating, and that's what happens. So for the low investment case here, I'm just highlighting in this blue line, that's the one we're looking at. And the reason why this occurs is because you accumulate so many people, and well, I think I have this on the next slide. So you end up in this collapse situation. You're extracting as much as you can to keep people alive, essentially. But the more you extract, the more resources required to get the next bit of extraction, and this is a sort of unfulfilled prophecy that's not able to occur. On the left side, again, is nature, the total amount of nature in the environment. And here I'm just pointing out that when you reach this physical constraint on extracting resources, defined by this net external power ratio, then it's not like you run out of resources. There's still resources out there, but again, it's just that you can't essentially afford to extract the last bit of the resource. You can't afford it in a resource sense or a money sense either. So what happens when you invest too slowly? The economy collapses because population reaches too high of a peak. too high in quotes here, but too high of a peak. And again, this is at the expense of accumulating more capital. Because I assume population will have some minimum resource consumption, so I don't let resource consumption go to zero for households, in the sense of if there were no food flowing to them or no resources, then they might just instantly all die. So I keep some minimum level that prevents them, that just has them dying at some maximum rate. The birth rates, or the death rates rather, are just some maximum number that's not infinity. So that keeps the population from dying instantly, so they have to decline slowly. And so when the resource extraction stops increasing, then extraction capital has to try to keep operating at its full capacity, because it's trying to deliver enough resources to households' consumption, because that's a constraint now. But it's unable to do this physically, because as resources keep getting depleted, a higher fraction of the resource is required to extract the next unit of resource. So it's trying to deliver more to households, but the more it extracts, the less it's able actually to deliver to the households. And
is a tipping point, Dr. King, from the availability of the natural resources, a tipping point from which, even though a high investment will anyway cause a collapse.
I'm going to show the results here from the high investment case that avoids this sort of rapid collapse, if that's what you're asking.
Yeah.
All right, so I'll get to that's after this slide. So essentially, the population doesn't decline fast enough. It goes quote unquote too high, and it doesn't decline fast enough to prevent this physical constraint. You could change the parameters, but essentially you could always find this type of result from the model, even if you change the
in a predator-prey model, this is an example where the predators have basically, they don't have enough prey to survive themselves, but they still have too many predators consuming too much prey, and it leads to a complete collapse. Is that correct?
I guess that's a good way to say it. Yep, I suppose. Okay, so what if you do invest fast enough in the system? All right, so you end up in this sort of quasi-steady state. So there are 3 charts here. I'm going to go through different phases of the simulation or the model results, kind of go through these different phases of operation in the economy. So I'll describe that using these 3 charts. The one on the left is the capacity utilization of goods. So this is there to just tell you, oh, this is how much the capital is operating. In the model, they operate a maximum of, or a normal level, if you will, of 85%. So that's why it's flat at the beginning at 85%. So that's the capacity utilization of the goods capital. In the middle is household resources consumption per person. So this is how much resources are left over, natural resources are left over to consume by people. And this is what dictates the death rates. On the right side is household goods consumption per person. So this is how much output of the goods sector is left over for households to consume. We could view both the center and the right picture as some level of welfare, our lifestyle in a very generic sense. Okay, so we'll go through, there's 5 different sort of steps here. So our phases. So there's kind of phase 1, and this is what they call in the paper normal economic growth. Capital is the limiting factor in output. Resources are abundant, and population's increasing. Everything seems fine. And so the thing to do here is just keep investing in new capital. You can extract more resources. All the capital keeps functioning. More people keep getting employed, et cetera. Everything seems to be working fine. Then there is this phase 2, which you reach a point, and I'm just kind of, in this particular set of slides here, I'm only paying attention to the solid black line, which is this high investment case. So phase 2, you now have an economy limited by labor. So you've invested in so much capital that there's not enough people to fill all the jobs. So you're at the maximum participation rate, and at that point you have to start reducing the amount of capacity utilization. So it starts to go down just a little bit there. It's hard to see, but it starts going down just a little bit. And on the right chart, you see this is at this point you've reached a peak in the goods consumption per person. So once you reach this condition, you start having to cut back on resource consumption that operates both units of capital. You also have, in the center chart, look at the solid black line again, it is approaching its minimum value. So it's hard to see at about year 60 to 70 there, the black line has essentially reached its minimum number, and that is what signifies phase 3. So I set this minimum number. The death rates are higher than birth rates at this minimum number. So the population is shrinking at some rate. So once you reach this threshold set in the model of minimum level of resources consumption per person, then it stays in this mode of operation for a relatively short period of time. And the economy is still limited by the amount of labor that's out there. But in this particular case, on the left side, in order to fulfill this condition, in order to allocate resources to households, you have to start cutting back on resource consumption by other things in the economy, and that's represented in the left chart. So the capacity utilization of the goods sector starts to go down rapidly because it's essentially saying, well, you're going to have to stop running goods machines as much so that they are not consuming the resources that can be allocated to people. And so this operates for just a short period of time, and then you end up in this phase 4 situation where the population has now declined enough to where the population is no longer at the limit, this minimum limit of resource consumption per person, but the capacity utilization still needs to decline in order to allow the rest of the economy to function. The far right chart shows that in order to keep the economy functioning and investing in new capital, so remember the economy is still investing in more capital because the assumption of capital investment doesn't change in the model, so it just keeps accumulating capital, and so it can't be used very much, which is on the left side. So the consequence of this is that whatever's left over in terms of goods for households goes to zero eventually. And then once it gets to zero, you're in a 5th phase of operation, in which you have to constrain resource flows even more, or in a different way. And so now goods consumption is zero, and not shown on this chart, the net investment declines to close to zero to facilitate operating all of the capital that's there, feeding the population now at roughly a steady state, and essentially, investing in the capital is required. Or you're not even able to invest in new capital because you have so much capital and have so many people that you're sort of maintaining at this point. So that's relatively complicated. I'll see if there's questions there. Go ahead.
Yeah. So I'm just trying to like have a great mental image. So your physical goods consumption per person, so that's things that, I mean, I don't know how does that. So you still have a population that's alive, right? And being sustained with some energy. They require energy. Because they have consumption that's needed. And I consider goods. I consider. So you don't consider like things like food products or anything like that as goods.
Sorry, I didn't hear the last thing you said. That counts as goods.
Food products as goods in your model, or they're not. It's just energy. Energy. There's a certain amount of energy, and that's just the energy for the human capital, or the households will consume. The energy they consume, the consumption per person is a piece that's conceptually just the amount of energy consumption to sustain life, and anything beyond that is like goods.
To some, almost yes, mostly, but I don't just allocate. I guess the population doesn't only receive a quantity of energy at the sort of level to maintain population, and then everything else becomes goods. The sectors have excess, if you will, for household consumption somewhat independently of each other. But the only thing that dictates death rates in this model is the nature consumption per person. It's feasible, and I have played with versions where both the goods consumption and the resource consumption both affect death rates, and that would be a probably more normal, more holistic way to do it.
Yeah, I'm just thinking of a real physical system of a person living someplace, right? You can't avoid, to live, you can't avoid goods consumption, some kind of goods consumption.
You can avoid, yeah, in this model, it assumes that you can avoid all goods consumption and you're just the same as if you didn't, I guess. So yeah, it's just qualitatively a lifestyle concept, I guess.
Dr. King, this is Tim. I know we're kind of running out of time, but have you ever compared these model results to historical examples? Because you may not have intended it, but I think you captured the collapse of Roman Empire in the low investment model. There's a lot of theories out there about energy and collapse, and just, I know we're running out of time, but I'd like to talk to you more later about that.
Right. Okay, yeah, so I'll try to get to that. And the answer is no, I compared it to the US contemporary system instead of Rome. So, so to get there, there's just last few set of slides, and I'll go through them quickly. On the left, so the middle is the wage share, and this is what I'll compare to the United States. And on the left is the depreciation share, the fraction of value added going to depreciation. So there's this transition period, again, paying attention to the high investment case, the solid line. So this transition period is essentially characterized by the time at which you reach the peak extraction per person, which is on the right. So there's a time in which resource extraction per person is going up, and then there's a time in which it kind of goes steady. And again, it goes steady because I'm assuming a resource like a forest that can regenerate. So there's this transition period, and you sort of have a time period at which there's a trend before the transition, and then there's sort of a broad trend after. And the wage share is roughly flat before this transition, and then it declines at some steady rate after that. So it's because you're increasing the depreciation share in this case, since that becomes a higher fraction of value added, wages here at the bottom are part of value added. And so the model is essentially assuming a capitalist type economy where net profit is sort of guaranteed by this price markup. Interest payments are something that have to get made, I'm assuming, like there's no bankruptcy. And the depreciation accumulates just because you keep investing in capital. And so wages are the only thing that can go down. So wage share is the only thing left to go down, and that's what happens in the model, or the way it's set up. And so, all right, does it match anything historical in the data? I showed the chart on the right at the beginning of the presentation, which is the black line is the wages and salaries as a fraction of GDP. The red dashed line on the right is energy consumption per person. The left chart is from the model, this high investment case scenario. The black lines represent wage share and another household income share, which could include the interest payments in this model. And then the red line is extraction of nature per person. So what's the point? They both have a roughly flat situation before extraction per person peaks and then declines afterwards in terms of the wage share. And of course, the resource extraction has a time where it's per person is increasing and then it goes flat. So this is qualitatively exactly the same in my mind. Here is another look at a similar set of metrics from the model. This is debt ratio. So on the right is the corporate and financial debt as a percentage of GDP in the United States since World War II. And on the left is the debt ratio of my model. So there is the transition period in both. There's the time before hitting peak resource extraction, and there's the time afterwards. And the time before, debt ratio is increasing, but at a slow rate. And the time after, debt ratio is increasing, but at a much more rapid rate. And so, again, without changing any of the rules or investment rules or other parameters in the model, only having this resource feedback presents these results. So there's no assumption and changes about labor bargaining power of wages. The wage function is exactly the same. There's no assumption of different rules or laws or taxes. I don't even have taxes in the model. There's no government. I still get this kind of result. So this is the final slide. The takeaway is, by consistently tracking physical and economic flows, this model hopefully can serve as a base concept to add other components that are interesting and important, government taxes, add other kinds of energy resource sectors like renewable energy or fossil energy, things like solar panels. And maybe you could couple this to, some simple model of climate and atmosphere to make an integrated assessment model. Models, by doing this, is able to explain or at least provide a physical resource explanation for coincident trends in energy flows and money flows like wage share and debt. and it shows how economic decisions, like the rate of investment, do inherently relate to the rate of physical resource consumption and population. So listed here is the title of the paper in Ecological Economics, and it just came out this week. So there's a link there that I could email if it's hard to copy those links. I didn't quite just put it on my website yet, but I will this weekend or today, because it just came out. So you can access the paper now, finally. So I'll stop there. I don't know if there's time for people to hang on for any other questions, but I have time.
Great presentation.
Thank you. So yeah, very good, insightful questions. That was, you know, I thought it'd be good to interact with this group because you would have a lot of, insights into the dynamics and.
What other predator-prey, for question-wise, what other predator-prey dynamics did you see or take away from this sort of treating resource as a prey rather than a carrying capacity or something like that? Because you could have taken, there's some models that treat the resource as sort of a carrying capacity, like water in the Sahel, or some, it still does regeneration, renewable. Did you find any real differences by using the predator-prey model versus a other model on how to look at resources?
I think I'm not able to answer that question just based upon understanding the other types of approaches you're referencing. I think I probably don't know enough about them to have much to say. One goal, is to add something akin to, let's just say, like photovoltaic or wind power as an energy resource, which might translate to this kind of water flow concept, or some sort of constant flow rate of solar power and converting it, or radiation. And so I haven't yet done that. And I'll take insights from any of you offline or on email. Once you do that, of course, you have to make a decision about how much of, if you got two different natural resources, how much do you extract of one versus the other, and you have to look at that kind of thing.
I'll send an email at a high level, though. It's just that renewable, and you know, the renewable resources, it doesn't matter how far it drops because there's a time in which it renews, whereas a regeneration resource, that's kind of like a breeding or trees. You need some existing from which is sort of breeding stock to grow others.
Right.
I'll send it on an email, though. Thank you.
Okay, yeah, it makes perfect sense. I think at this point I don't have a lot of insights into the, so you probably have the insights to tell me, so thank you.
Yeah, I think I was just thinking about Tim's question about having, looking at it from a carrying capacity perspective. I think there's some fundamental differences in the nature of the biological systems that it showed these, like, sigmoidian kind of patterns, stuff like that. As you're eating, I mean, you have to eat food, and otherwise you die pretty rapidly if that food source goes away. Whereas you don't have the same sort of time. You have different time horizon, time delays in the system related to extraction of energy sources, that could contribute to a collapse. The density of the energy source or the nature that you're extracting from, you don't see it really, right? Because you're not observing it directly, you're not measuring it, you're not metering it out.
Well, I mean, that all gets to the structure of the model. Conceptually, you're correct, but I think it gets to how you model it with the specific structure. So,
well, it's just like the fish stocks, right? Why did the fish stocks collapse? Because you don't see that below the surface that you have a density function. Once you get below a certain density function.
Right, but the density function, that is a specific factor of the regeneration stock. So if you have a renewable stock, you do not have it's less of a density function and more of a time delay. And that's some of those differences I was getting to that we can take offline, but create different dynamics. A renewable resource, even if the density goes to zero, will return because it's being renewed from something. There's some outside the model thing that causes it to renew. Whereas a regeneration stock, if the density goes to zero, you're at zero. And both of those are interesting.
Yeah, so I hope to, I'm excited to hear about your insights, because that's one of the places I wanted to go. And investing in something like, let's just say wind or solar panels, I imagine, the delays that you're speaking of will come into play. If you invest in them enough early, then you may avoid a certain situation, and if you invest in them too late, then you won't.
Yep.
Thank you, Dr. King.
Thank you, Dr. King. Great presentation.
Thank you very much.
Okay, thank you, everyone.
Okay, I'll stop the recording now.